Hey guys, my name is Jason with Mount Baker Mining and Metals, and on today's video we're going to look at a sample that was sent to me from Sierra Leone in West Africa, and we're going to kind of analyze the sample. I'm going to do a rough fire assay on it to try and determine the value of the sample, and then I'll walk you through those steps, and then we'll send some other samples off for a professional fire assay so I can kind of check myself. Here's the stuff we're going to be working with today, and this is concentrates from hard rock ore, and they've gone through at least one concentration, and this is the sulfides and the heavy mineralization in the tailings after concentration. And so we're going to try and figure out how much gold is left in this stuff after the miners have used everything they can to get what amount of gold they can out of it. So hopefully we can determine how much gold is left in this. So before we get started digging into our sample, I've taken out 3 separate assay samples here, and I'm going to send these off to American Analytical in Osborne, Idaho, and they're going to run a professional fire assay on them and give us the results. And if I don't have the results by the time this video is posted, when I get them, I'll post them in the description below, so check back to see the results if I don't have them right as the video comes out. Okay, so one of the first things we're going to do is we're going to measure out for this first smelt, or assay I guess, we're going to measure out 100 grams of material. I've got my scale zeroed here. I've got my material all mixed up, so we're not getting a bunch of the stuff that's settled out in the bottom or something. I've got it all mixed up. I've added a little bit too much here. But as you noticed from before, it's all sulfides. It's pretty much a pure sulfide concentrate. And so we're going to have to use a little bit of chemistry to remove the sulfur and get it into a form that we can dissolve in our slag. So all that sulfur goes away, all the matte that we should have go away, get dissolved in our slag, and so we're left with 2 phases, a slag phase on top and a metal phase on the bottom. So there's my 100 grams of sulfides. Now we're going to mix up our flux. And because this is a sulfide-rich ore, we're going to make it very basic. And to do that, we're going to use soda ash. And so I'm going to mix up, what I found is about a 1-to-1 ratio of flux to sulfide ore works pretty good. And I'm going to use soda ash, 75 grams of soda ash, and 25 grams of silica sand. And so we'll have 100 grams of flux and 100 grams of sulfides. And the soda ash makes it real basic, so it'll absorb the iron sulfide that we're going to make. And the silica protects the fire clay crucible I found. I found if you don't use any silica, your crucibles get eaten up really fast. But if you add too much silica and or too much borax, the slag becomes so acidic that you have a matte layer, and it's not basic enough to absorb the matte. So again, this is what I found works really well for me. Now we've taken our silica sand, our soda ash, we have 100 grams of that mixture. We're going to combine it with our sulfides. I'm going to put a lid on it here and then get it mixed up really good. And so I don't know if there's lead sulfide in here, iron sulfide, arsenopyrite, chalcopyrite. There could be a whole suite of base metal sulfides in here. And our job is to get rid of all that stuff and see if we can collect metal at the bottom. Now we're pretty well mixed up. Let's see if I can show you this from across the table here. But it's pretty well mixed up there. So now I'm going to take just a fire clay crucible, pour our mixture in there, and this is where some of the heavy chemistry comes in. I'm going to add some nails. Just iron nails, steel nails. I just went and buy them in the hardware store. I'm going to put, I don't know, 4 or 5 in there. And what the nails do, I put the heads down as well so that they have the most exposure to the sulfide mat that forms at the bottom of the crucible. And what those iron nails do is the sulfur is very much attracted to the iron. And so if you have a molecule of galena, let's say, a lead and a sulfur atom, as soon as that galena molecule touches the iron nail, it'll pull the sulfur off of that molecule and reduce it to lead metal, which is going to sink down to the bottom of our crucible. And it's going to form iron sulfide, FeS, which is FeS, iron sulfide. And when that forms, because we have such a basic slag from our soda ash, we put a lot of soda ash in there, that iron sulfide is actually going to get dissolved up into that slag, and there won't be any mat. And so if there's galena or lead, copper, arsenic, any of that stuff, we're going to reduce all that to metal. We're going to have all that replaced with iron sulfide, and then the iron sulfide is going to get dissolved in the slag, and we'll have a little metal button at the bottom if there's enough. Now, this first one, I'm not going to add any collector metal and see if I can just reduce the base metals that are in here and get a metal button at the bottom. If this first one doesn't work, I'm going to do the exact same thing, the exact same recipe, but I'm going to add some lead oxide to it, some litharge, and that will act as our collector metal if we need it. So we'll see how this first one goes, and then we'll decide if we need to add any more collector metal. This is a very quick walkthrough of our furnace. I have a blower here. It's just a shop vac hose going down the little manifold here where the propane mixes in and blows into the furnace. This is just KO wool that's wrapped into a cylinder. It's seen better days, but it still holds heat. So I put my crucible down in there, blow in there a bunch of hot air and propane. It mixes, burns, gets about 2200 degrees Fahrenheit. When all that's molten and cooled, molten and hot, we're going to pull it out. We're going to pour it into our cone mold here. The metal, this is just an inverted pyramid. The metal is going to go down to the very bottom. The slag is going to sit on top. And once that is cooled, we can knock it over and there should be a little metal prill on top. All right, guys, a couple of things to notice on that first pour. I don't know if you could tell from the video, but when I was pouring it out of the crucible into the cone mold, it was really, really thick. It was really kind of soupy, and it didn't pour very, very well. So that was my first indication. The next indication was when I tipped that cone mold over and it was cool and it was all glassy. The slag shouldn't look glassy if it's a basic slag. And so that told me I didn't have enough flux in there to completely eat up all the sulfur and the iron sulfide that we made. And so we had that matte layer at the bottom. You saw that matte. I don't know if you can see it in the video, but there was a significant amount of matte in the bottom. And what that tells me is there's so much sulfur in that ore that we need to get more basic flux in there to absorb that. So what I've done on this next one is I've doubled our flux. So I have 200 grams of our mixture. It's 150 grams of soda ash and 50 grams of silica sand. So I have twice as much, still the same 100 grams of sulfide concentrates. And then I've added 50 grams of litharge. That's the lead oxide. I've added 8 nails this time instead of 4. You saw I had to add 4 more nails on that first pour because they got eaten up so quick. So I have 8 nails in there. Hopefully, these birds. Hopefully we have enough flux in there to pull out all that sulfur, iron sulfide that we make. The litharge will hopefully reduce to lead, come down and collect in the bottom, and we'll have a nice metallic button. And hopefully on my next shot, these birds will be out of here, so I won't be fighting with the bird sounds. So anyway, let's see what happens on this next pour. Okay, well, we got our bead. This is that 35-gram lead button that was at the bottom of our cone mold. And hopefully what happened is the lead went down, collected all the gold and silver, and now it's in this little prill. So now what we're going to do is go over to our cupelling furnace. I'm going to put this in a cupel, and the lead is going to oxidize at a very high temperature. The furnace is set at about 1850 degrees Fahrenheit. That's going to melt the lead, and the lead is going to oxidize in the oxygen-rich environment in the atmosphere. At 1800 degrees or 1850 Fahrenheit, that lead oxide is molten, and so it will start to roll off that liquid lead bead in the furnace, and the lead oxide will be absorbed by the cupel. It's a little magnesia cupel, and that's going to continue, and even a little bit of copper or a little bit of arsenic or a little bit of bismuth is going to also roll off there with the oxides. And as that thing goes all the way to completion, this little bead is going to be left with just the precious metals, the gold and the silver that won't oxidize in the atmosphere even at 1850 degrees. And then we can cool that down, pick the bead out, get it weighed, and then we'll figure out how much precious metals we have in our 100 grams worth of sulfides we started with. All right, so we got a nice little bead here. Get it out of there. There we go. And I don't know if you can tell, but it's definitely a little gold colored, so it's probably 60% gold or so. The rest would be silver. So let's see what we got for a weight here. .047, so 0.05 of a gram. One more thing I'll mention here real quick. Now that it's cooled down, you can see in the cup of that cupel, that real yellow, lemon yellow color is from the lead oxide. And then right there around the bead is that dark greenish black. That's either iron that was contamination in the bead or a little bit of copper that was contamination in the bead. But you can kind of tell from the oxides what the bead has in it. But that's not a bad little bead for just a 100-gram sample. That's actually pretty good. All right, so let's do a little math here, and I'm doing this in real time, so bear with me. So we recovered 0.05 grams AU and AG. We started with 100 grams of material, and we're going to find out how many grams per ton we have. So there's 1,000 kilograms in 1 ton, and we have a tenth of a kilogram, and so we have 1/10,000th of a ton. So if you multiply that number by 10,000, I think you get 500 grams per ton, per metric ton. And we figured, judging by that color of the bead, it was about, let's call it 3/5. So we're going to say there was 300 grams of AU per ton. So that's not too bad. All right, so let's talk a little bit about what we figured out. So we found out that in the first one, we didn't have enough basic flux. And so I added twice as much flux to the second round with lead, and that's where we ended up with our 0.05 gram bead. The other thing is we added 50 grams of lead and ended up recovering 35 grams. So we lost a little bit of lead, which is okay, but we didn't amass a whole bunch more material. It wasn't like we ended up with a 75 gram bead. And we also didn't get a bead from the first smelt we did where we got the matte. So what that tells me is there's not a lot of other base metals, sulfides in there. There's not a lot of galena. There's not a lot of chalcopyrite. We're not getting a bunch of additional lead. We're not getting a bunch of additional copper. And so what that tells me is this is probably a form of sulfide where there's a lot more sulfur than iron. And so as we add in additional iron in the form of nails, we pull that sulfur, that extra sulfur off, end up with just that pure form of FeS sulfide, and that's what gets absorbed into our slag. So it's actually nice and good that we don't have a lot of other base metals we have to worry about with the cupelling process, because if you have a bunch of copper in there, or if you have a bunch of arsenic in there, or tin, it's a lot harder to cupel away. So it's actually an advantage that it's just iron sulfide that we're working with. So what I want to do now is taking what we found out from our first 2 smelts. I have another one in the furnace right now. I'm just copying the one we did at the very beginning where 100 grams of ore. I've put in 200 grams of flux this time so we can hopefully get all that matte absorbed. I've added 8 nails and no lead. So I want to find out if we have enough metal, either gold, silver, and a little bit of base metals, that we can collect it all down at the bottom of the crucible and then again in the cone mold without using any lead as a collector metal. Well, we just did that last smelt with no collector metal, and there was no bead in the bottom. It was a nice slag all the way through. There wasn't any matte. It was a real uniform slag. So there's just not enough precious metals in there to collect down at the bottom into a little bead. And so we're going to have to use some sort of collector metal to go forward and to collect this stuff if you're going to do smelting on a commercial size or commercial basis. And you can either use bismuth or lead. And my experience has been actually that you can just take a piece of metal and put it at the bottom of the crucible. Take 100 grams of lead, put it in there. You don't need to use fancy stuff and litharge and lead oxide and reduce it down to lead metal. Just do 100 grams of sulfides, 200 grams of our flux recipe, put in 20, 30, 50 grams of lead, and smelt it. And the lead at the bottom should do the collection. I think how that works is the lead forms a little bit of a pool at the bottom of the crucible, and the slag on top has the metals as it's melting. And as that slag starts to flow and go around in convection, as those little tiny particles of metal come down and touch that molten pool of lead at the bottom, or bismuth, or whatever collector metal you're going to use, they would much rather be in that pool of liquid metal than floating around in the slag as little tiny beads. And so as soon as they touch that pool, they suck into that pool of collector metal, and you're golden. You don't have to have litharge that you reduce to little metal beads throughout. Whoa, sorry, I got a phone call there and it cut off my video. But anyway, I think I was saying that you don't have to have all these little tiny beads of lead suspended in the flux and then rain down through the crucible as it does its thing. My experience has been you just put that collector metal right in the bottom and it does just fine. So the next question is, how much gold or precious metals do you actually need to smelt? And so I did some math and worked through this. If you smelted, I think my math is right, if you smelted 10 kilograms of this stuff, you'd end up with about a 5-gram bead or about 3 grams of gold. And so I got to leave it up to you guys to decide if that's enough. But this stuff is right on the edge of where it kind of needs to be, in my opinion, of making it worthwhile. I would like to see about 5 or 10 times more gold in a concentrate to smelt it. This stuff has 0.05 grams per 100 grams. I'd like to see, a half a gram per 100 grams, about 0.5% to 1% of precious metals. Kind of, in my mind, makes it worth all the while of screwing around with crucibles and heating it up, and the propane or the fuel and the consumables and cupelling and all that stuff. And interestingly enough, I forgot to mention this earlier, I found that it takes about 1% is the very, very bare minimum, lowest amount of precious metals that you can collect in the bottom of a crucible or a cone mold without a collector metal. So if this stuff had 1 gram of gold in it per 100 grams, you might be able to get a bead in the bottom. But if you have 5 or 10 grams, 5%, 10% precious metals, then you really don't even need to use a collector metal. It can just come down into the bottom on its own. There's enough mass of precious metals to collect at the bottom of the crucible. So what do you guys think? How much gold and precious metals do you need to make it worthwhile? Is it a dollar amount? Is it a gram amount? Is it a percentage? Does it matter if you can do a huge smelt, or would you rather do 5 small smelts? Leave me a comment in the comment section below and let me know what you think for that. But I'm going to stop this video here. I think we've come to the conclusion that there is some gold in this stuff. There's enough gold in there that it might be worthwhile for those guys in Sierra Leone to go after. And one other thing I've been thinking about is this is concentrates that they've already removed all the free gold they can get out of it. And they have, I'm making up a number, but let's say 30% of the gold is left in the concentrates that we smelt out. But if they left it all together and they smelted it as a whole, they could recover the 70% they're already recovering, plus an additional 30%, and smelt it all at once, so you're not having to screw around with mercury and amalgamating it and processing it 2 or 3 times. If you just take it right off your sluice box or your concentrator, smelt it, you can recover more gold, the gold that they're already getting, plus additional gold, and silver as well, if that's of any value to them. But there may be a way rather than collecting the precious metals that they can get and then trying to smelt the stuff afterwards. Just do it all in one step, and it might make it worthwhile at that point. So it was an interesting video. It's fun to always take a sample that I've never seen or played with before and be able to kind of crack that nut and figure out how to process it and get the precious metals out of it for them. So I hope you guys enjoyed the video. Let me know what you think with a comment in the comment section. Otherwise, thanks for watching, and we'll see you on the next video.